Hello, my dear students. Today, I'm sorry. Today, I would like to offer control work. Um, the first control work on the first and second laws of thermodynamics. Well, this control test consists of two problems, and now I'm going to show you the first of the two. Here it is. So calculate the change in internal energy, entropy, and other thermal as a correct potential, or Helmholtz energy, when 1 mole of under gas is expanded from 20 liters to 200 liters at 27 degrees Celsius. And the same is applicable to 1 mole of van der Waals gas. And the values of the constants A and B are given as well. Well, let's start from the first part. It's part A. So what can we say? We understand that the temperature is constant, right? So, and that makes the solution of the problem much easier to deal with. Well, because of the constant temperature, we understand that any change in temperature equals 0. And that immediately gives us the brilliant opportunity to calculate the change in internal energy of the process. We remember that differential of the internal energy equals CV times dt, right? Of course, times the amount of the substance, but we know that it equals 1. However, dt equals 0. That's why du equals 0. That means that the change in internal energy for that process equals 0 too. So we also can calculate the change in entropy. Yeah, of course we could write down the needed formula immediately, but it's not the best way to show the examiner that you know the stuff. Let's derive the formula. From the definition, we remember that ds equals delta q over t, right? According to the first law of thermodynamics, we can write that dq equals du plus p times dv over t, right? But again, from this problem, we remember we have already found out that du equals 0. That's why we can write that it equals p times dv over t. Okay. Also, we've got v under the symbol of differential, and that makes the operation isn't very convenient to deal with. And in order to make it, how to say, more or less attractive in integration terms, so let's remember that we deal with an ideal gas, and its equation of state is P times V equals R times T, right? That means that P over T equals R over T. For that reason, we got that ds equals R V times dV, R over V times dV. Or we can put V under the differentiation, and we will get R differential of natural logarithm V. Now we can integrate delta S equals integral from S1 to S2. These are what we know integration limits of ds, right? And that equals R dlmv from V1 up to V2, but R is constant, And that means this formula. This is the final formula. Of course, we should write down the symbol m, which means that we are making we are calculating for 1 mole, and that equals joules per mole per Kelvin. Natural logarithm 200/20. Okay, and that gives us 19.14. Yeah, that's the answer. It's not an answer. Okay. Now they also want us to calculate the change in Helmholtz energy. So we remember that delta F equals delta U minus T times delta S. Okay, but that equals 0. Okay, and that means that we got minus 27 plus 273. So we transform Celsius into kelvins, and we multiply to 19.14, and finally we'll get minus 5,743.1. I'm sorry, joules per mole. We could have got the same, and we could have got the same answer if we remembered another thing, that that dF equals minus S times dt minus P times dV, right? But we remember that T is constant. For that reason, dt equals 0, and that component equals 0 too, therefore. And we've got the following, that dF equals minus P times dV. Okay, and that means minus RT over V times dV. Now we can integrate right? But R and T are constant. So and finally we've got the same answer. Yeah, I can write. So these are the answers to these questions if we deal with the ideal gas. Now let's do the same for van der Waals gas. Let's do the same. Okay. So it's B. It's B. Now, what can we say? First of all, let's write down the equation of state for van der Waals gas. It's P plus A over B squared times V minus B, that equals R times T. Now we remember that when we deal with van der Waals gas, we can't neglect the potential energy. In other words, we can write that U equals the sum of kinetic energy plus the potential energy, the energy when the particles which make up the gas they attract each other and they expel each other. Okay. Also, we should understand that the differential of the kinetic energy equals CV times dt, but as the temperature is constant, that equals 0. As for this one, the potential energy. So the potential energy equals the work which should be done in order to pull a particle away from the system at an infinite distance. In other words, we can write that it's minus P inner pressure, which equals this, well, times to B. That equals A over V squared times dV. And if we integrate it, we will get that the potential energy equals from V to infinity A over V squared dV. It's easy to do. So when we've got infinity in the denominator, so that equals 0, right? And finally, we've got minus A over V. Okay, and that means only one thing, that delta U for van der Waals gas equals CV times delta T minus, of course, times nu, minus A mu squared over delta V. Okay, delta V. But again, this element equals 0 because the process is at constant temperature. And we can write like this, or we can put the minus 1 into the brackets, and finally we'll get this expression. This is the formula which allows us to calculate the change in internal energy for van der Waals gas. Okay, let's do that. So the value of A is given, it's 2. It's 2 atmospheres liter squared over mole squared 1 mole squared 1 over 20 minus 1 over 200 liters raised in the minus first degree, and we get um, 0.09 atmospheres per liter, right? And we can express it in joules per mole, and that means that it equals 9.12 joules per mole. This is the answer concerning the change in internal energy of an balanced gas. Now, as for entropy, so let's remember that ds equals dq over t, and that means du plus pdv over t, right? But we remember that du, not remembered, but we have previously worked out the dependence of the internal energy U on temperature for van der Waals gas. So, and it equals minus that, no, CV times T minus A V, okay? And if we differentiate it, because we need the differential of internal energy, so we will get CV times dt plus A over V squared times dV. Okay. Now, from this equation, we can write that P times dV equals RT over V minus V minus A over V squared times dV, right? Okay. What did we do in this case? We just expressed P from this equation and rewrote it here. Now we can plug in all these formulas into this this one. So ds equals cv times dt plus a over v squared dv plus, now I'm writing this, rt over v minus b times dv minus a times v squared times dv and all the sum over t. We see that we can make this expression easier to deal with. Okay, and we finally get cv times dt over t plus rt over t times v minus v times dv. Finally, we've got this one. But again, remember that the process, the expansion occurs at constant temperature. That's why this part equals 0. And finally, we can integrate. So delta S equals we can write like this as well, from V1 to V2. And that gives us the final formula. So let's plug in the values. It's clear that it won't change a lot. So it equals 19.15 joules per mole Kelvin. This is the answer. As for delta F, again we can use this formula. It's delta U minus T times delta S, right? But we have calculated delta U, which equals 9.12 minus the temperature is 300 kelvins times 19.15, and we got minus 5,736.2 joules per mole. This is the final answer. So these are the answers related to van der Waals gas. As you see, the numerical values are not different very much from the ones we've got for ideal gas, but still there are some differences. And the technique of calculation is slightly different because the equation of state is different. It's not typical ideal gas state equation. Thank you. Now let's proceed to the second assignment. Hold on a second, please. Hold on a second. I'm copying the assignment. Here it is. Yes, here it is. So they ask us to calculate the change in enthalpy, internal energy, entropy, Gibbs energy, and Helmholtz energy for a given reaction at a given temperature, and the atmosphere is equals 1 atmosphere. Also, I just want to draw attention to the fact that heat capacities of both reagents and products of the reaction are linearly dependent on temperature. In other words, we cannot consider the values of the heat capacitors given as constant values. No. That means that we will have to do something about it. But what? That's the question. Okay, we'll try to do something. So first of all, let's use Hess law in order to calculate the change in enthalpy of the reaction at temperature 298. R stands for reaction, and we are calculating the effect of the reaction at this temperature. And according to Hess law, so we can write that it equals the sum of enthalpy formations of the products. That means H2O enthalpy formation at 288 plus that of this substance C3H6O2 minus the enthalpy formation of carbon dioxide minus double enthalpy formation of methane. We shouldn't overlook the importance of this coefficient too. That's why I have doubled this function. Okay, and let's plug in the numerical values given in the table. Thus we got minus 0.83, okay, minus 0.57, minus over minus gives us plus 393.52 plus 2 times 74.87, and that gives us 83.86 kilojoules per mole. Okay. Now, again, the heat capacity of the substances of this reaction are linearly dependent on temperature. And that means that we don't know how to deal with them. The only idea given as a hint for our consideration is this one, linear dependent. That means that we can write Cp like a function a plus b times t. That means, in mathematical terms, what is written here? Linearly dependent on temperature. Linear dependence on temperature is expressed through this equation. In other words, for each of the 4 substances, we're supposed to find their own coefficients A and B. Let's do that for methane. So we can write that the heat capacity of methane gas equals A plus B times T, right? And now we're supposed to find these 2 coefficients A and B. Let's take a look at these values which we have got, which are contained in this table. So we can write that for temperature 298, we can write that capacity 35.70 equals A plus 298 times B. Also, we can write that the capacity of 49.60 equals A plus 800 times B, because this value is corresponding to temperature 800 kelvins. And we've got the system of 2 linear equations, which allows us to calculate the values of A and B. I guess you know how to do that. I will write down these values. I have already calculated them. For methane, A equals 27.45 and B equals 0.0277. You should understand that A for methane, B for methane. And doing likewise, we can calculate. In other words, we can write that for for methane, we've got the following temperature dependence: 27.45 plus 0.0277 times T. Now we've got it. Okay, let's do the same procedure for the rest of the substances, participants of the reaction. For example, for CO2, we've got the following system. 37.14 equals A plus 298B and 45.60 equals A plus 800B. So, and finally, we've got for carbon dioxide heat capacity, the following equation: 32.12 plus 0.169 times T. Likewise, we've got the heat capacity of that substance, organic substance. Oh, I'm sorry, it should be only one O. That gives us the equation of 52.40 plus 0.0755 T, and the equation capacity of water vapor. This equation is the following: 32.18 plus 0.0048 times T. Yeah, and now I guess that we are ready to calculate delta Cp for the reaction using the same algorithm. So we add Cp equations of the products, and then we subtract from the sum the sum of the Cp equations of the reagents, taking into consideration the coefficients. So again, we can write like this: Cp of products of finals minus initials. Okay, and I won't go. I won't write down all these long expressions. I will write down only the final. It's minus 2.44 plus 0.0512 times T. Okay. Now we also can use the Kirchhoff law. It's integral form. So at temperature 598 equals integral from 298 to 598 delta Cp for the reaction dt times dt. So we have calculated this. Where is it? Here it is. It's 83.86. But these are kilojoules. That's why I will multiply to 1,000 plus And instead of this, I'm writing down this equation, final minus okay. And that is very easy to do. So that will be equal minus easy integration. Squared minus 298 squared, and that will give us the value of 90.01 kilojoules, or just 90.01 kilojoules. Okay, then let's continue on it. Area. Okay. So let's continue. We remember that delta H equals delta U production plus delta P times V, right? Yes, we remember that. Or that means delta nu of direction times R times T. In other words, we should calculate the difference between the sum of the coefficients of the products, and we should subtract it from the sum of the coefficients of the reagents. If we take a look at the reaction, we will see that delta nu with index R equals -1. But we need this one. First of all, let's express it from the formula, from the equation. Okay, we have already calculated the enthalpy, the change in enthalpy. So it's 90.01 times 1,000, okay, minus, and delta nu with index R equals -1, and temperature is 598, and that gives us the value of the change in internal energy, 94.98 times 1,000 joules, or 98.98 kilojoules. Okay. Now, the change in entropy. At temperature, we can also write it here. Reaction over T times to T. First of all, let's calculate the value of the first term of the equation. Delta S of the reaction at 298 degrees equals S of water vapor plus S of the organic substance minus S of carbon dioxide and minus double S of methane. So that equals 72 plus 994.93 minus 213.67 minus 2 times 186.26, and the final is minus 102.54 joules per mole per Kelvin. As for this integral, it's very easy for calculation. Instead of delta Cp of the reaction, so we can write down the equation which we have derived previously. It's minus 2.44 plus 0.0512 times T over T times the T, and that means times natural logarithm of 598 over 298, okay, plus 0.0512 times 598 minus 298, and that term equals 13.66 joules per mole per Kelvin, and that means that the change in entropy of the reaction at temperature 598 equals minus 0.54 plus 1366, and that gives minus 88.88 joules per mole per Kelvin. Now, as for the change in Gibbs energy, so we can write that it equals this term minus 598 times the change in entropy of the reaction at the same temperature. So let's plug in the values we have already calculated. It's 90.01 minus so that gives joules per mole, or 143.16 kilojoules per mole. As you see, it's positive. That means that at these conditions, the chemical reaction cannot go itself forward, cannot. It goes backward, but not forward. And also, they want us to calculate the change in Helmholtz energy. Okay, we can do it. We can do it using this formula, well-known formula. Mm-hmm. In that case, sorry, kilojoules per mole. So these are the answers to this problem. I hope that the solution way is clear to you. If it's not that clear, so feel free to write to me in the comments. I will try to explain it in more detail. Thank you very much for your attention. Goodbye.